Time and space complexity are two fundamental concepts in computer science used to analyze the efficiency of algorithms. They help determine how well an algorithm performs as the size of the input grows, making them essential for designing optimal solutions in data structures and programming. Time complexity measures the amount of time an algorithm takes to complete its execution based on the input size, usually represented as n, instead of calculating the exact execution time, which varies due to hardware and system differences. Time complexity gives a machine-independent estimate of performance. It is commonly expressed using asymptotic notations such as big O, big omega, and big theta. Big O notation represents the worst-case scenario and gives an upper bound on the running time. For example, linear search has a time complexity of O n, while binary search achieves O log n. Big omega represents the best-case performance, and big theta provides a tight bound when both upper and lower limits coincide. Time complexity becomes especially important when working with operations such as searching, sorting, insertion, and deletion in data structures like arrays, linked lists, trees, and graphs. Understanding time complexity helps developers compare algorithms and choose the most efficient one for large datasets. For example, sorting algorithms differ widely in performance. Bubble sort is O n squared. Merge sort is O n log n. And counting sort can achieve O n under specific constraints. Algorithms with polynomial or logarithmic complexity grow more slowly, making them preferable for large inputs, while exponential or factorial complexity quickly becomes impractical. Time complexity also helps identify the effect of nested loops, recursive calls, and divide and conquer strategies. Recurrence relations, such as T n equals 2T n 2 plus n for merge sort, help determine the overall time complexity of recursive algorithms. As a result, analyzing and minimizing time complexity ensures fast and scalable systems. Space complexity, on the other hand, measures the amount of memory an algorithm uses relative to the input size. This includes memory for input variables, temporary variables, recursion stack, and data structures created during execution. Space complexity is commonly expressed using big O notation to indicate the upper bound of memory usage. For example, an algorithm that creates an array of size n has a space complexity of O n, while a constant number of variables results in O 1, known as constant space complexity. Space complexity is crucial when working with memory-constrained environments such as mobile devices, embedded systems, or algorithms that handle large datasets. Recursive algorithms often require additional space for function call stacks, which increases their overall space complexity. For instance, the recursive version of the Fibonacci algorithm uses O n space due to stack frames, whereas its iterative version uses only O 1 space. Similarly, data structures influence space requirements. A linked list needs extra memory for pointers, while arrays require contiguous memory blocks. Efficient algorithms aim to minimize both time and space usage, though sometimes a trade-off is necessary. For example, dynamic programming reduces time complexity by using additional memory tables. In summary, time and space complexity are vital tools for evaluating algorithm performance. They enable developers to predict scalability, compare different solutions, and choose algorithms suitable for specific applications. By understanding these concepts deeply, one can design faster, more efficient, and more memory-conscious software systems.